Interesting meeting. And thanks to Pete for lending me his laptop and also providing a lot of background which applies to his talk and my talk both. First of all, a little bit about radial basis functions. They're basically similar to other spectral methods in that the function is approximated by a series with some coefficients lambda j multiplied by basis functions phi sub j. The difference is that with RBFs, all the basis functions are the same except for translation. They all depend upon a univariate function, phi of r, which is called the kernel. And the argument that distinguishes one from another is the absolute value of the distance from a point x to another point cj, which is referred to as the center of the jth basis function. One advantage they have over ordinary polynomials is that if you take an arbitrary distribution of points and try to do polynomial interpolation, sometimes it fails. But under very mild conditions on the kernel functions, it's been proven that RBF interpolation never fails. Experience and theory indicates that RBFs can converge with spectral accuracy even when applied on very irregular domains with very non-uniform distributions of data. In consequence, they become extremely popular for scattered data interpolation in a lot of different branches of science and engineering, and they become very popular in computer graphics. There's a whole lot of RBF species, but they, broadly speaking, fall into three groups. I'm going to concentrate on the spectrally accurate ones. And specifically, the barotropic vorticity model I'm going to talk about uses Gaussians. The RBFs and spectrally accurate RBFs in general all depend upon a width parameter. And the absolute width parameter turns out to not be very interesting. What matters is the width of the radial basis functions relative to the average grid spacing. The normal practice is to keep that parameter alpha constant and then take the limit as h gets smaller and smaller and smaller. The work that I've been doing over the past 5 or 6 years has gone along two parallel tracks. One is to develop a Lagrangian Gaussian RBF vortex blob solver, which is the first thing I'll talk about. But I've also done a lot of work on the fundamentals of RBF approximation. And there are a couple of reasons for that. One of them is that RBF theory, even after 30 years of development, is probably still extremely immature compared to finite differences or finite volumes or Chebyshev and Fourier spectral methods. And so there are a lot of gaps in the theory which are kind of fundamental to being able to use these methods effectively for big problems. A second reason is a little more peculiar. At Michigan, I'm sort of expected to work with undergraduates on research projects. And it turns out that RBFs lend themselves extremely well to undergraduate projects because the basis functions are all Gaussians or something equally simpler that you learned about in high school. It's possible to make RBF programs to solve partial differential equations that are only a couple dozen lines long. My former student, Natasha Flyer, one of the leading authorities in the field, likes to rub in the programming simplicity of RBF by including entire programs for PDEs in her papers, which would be unthinkable with any other method. So over the past few years, I've written, 8 or 9 papers with undergraduate co-authors. Well, the barotropic vorticity equation I've written out in Cartesian coordinates for simplicity, but we actually solved the problem in honest spherical coordinates. The vorticity is represented as a series of overlapping Gaussian vortices. Historically, vortex methods began with the work of Rosenhead in 1932 using point vortices. But for representing smooth continuous distributions of vorticities, point vortices are horrible because you're basically approximating it by a collection of delta function-like spikes. So in most fields of fluid mechanics, there's been a shift to blobs. And one of the popular shapes of blobs is Gaussians. So that long before RBFs became part of the popular lexicon, vortex modelers were in fact doing Gaussian RBFs without realizing it. It's a Lagrangian method, so the blob centers are advected with the current. The Poisson equation is solved analytically by superimposing the exact explicit solutions for Gaussian forcing, and I'll talk more about that on the next page. The blobs don't have to be of uniform size, but for convenience we usually take them to be the same. And when there's no wave physics present, vortex methods are terrific because advection gives a kind of automatic adaptivity. And furthermore, you only need to put the vortex blobs where there's actually like vorticity. So the dead zones of negligible vorticity have no numerical degrees of freedom. So in many problems, you've effectively reduced the dimensionality by 1. One serious technical problem is in order to solve the Poisson equation analytically, you need an analytical solution for the response of the stream function to a single localized source of vorticity. This answer for a point source on the sphere was found about 30 years ago. And since then, there's been a steady stream of papers of point vortex activity on the sphere. But there has not been the transition to vortex blobs as there has been in most other branches of fluid mechanics, because until recently, there was no analytical solution. But fortunately, I and my student Chung Zhou were able to find one. I haven't bothered to write it down because it's rather messy, but it doesn't involve anything more exotic than the exponential integral. We also, in our paper, give an approximate solution derived using the method of matched asymptotic expansions that's accurate enough for most numerical purposes and a lot faster to evaluate. And the idea is that to solve the Poisson equation, we calculate the coefficients of the RBF expansion of the vorticity by inverting an interpolation matrix. Then we take the solution, the analytical solution for a single RBF, and then we construct the general solution by superimposing all those particular solutions with coefficients that are the RBF coefficients of the vorticity. The potential vorticity is conserved on each moving blob, so the samples of the vorticity that go into the interpolation problem never change. Nevertheless, we have to recalculate the vorticity coefficients at every time step because the centers, the points that carry those unvarying values of the potential vorticity are constantly moving relative to one another. We end up with a system of ODEs in time to describe the movements of the centers of each blob. And to calculate these, we have to take the stream function and then we differentiate it to get the usual velocities. Now, there is something very unfortunate in these summations. Although we're working with Gaussian RBFs with vorticity, which are very strongly localized, the response to a localized forcing in the stream function is very unlocalized. And that's true even for point vortices in the plane, where a delta function source of vorticity gives rise to a velocity field that's only going down like 1 over the radius. The short-range interactions, that is to say the interactions between blobs which are close to one another, have to be evaluated by direct summation. However, the long-range interactions can be summed very effectively by using tree codes and fast multipole methods and things like that. One of the happy situations is that the analytical solution for Gaussian forcing tends exponentially fast to the analytical solution for point vortex. So we can apply Robert Krasny's marvelous tree codes to our problem as effectively as they can be applied to the point vortex models that Pete was just discussing. So the summations are not the big killer. We can deal with those pretty effectively. The rate determining step is the cost of calculating the coefficients of the vorticity. Okay, we've done a few case studies, but this work is still in progress. The graduate student Li Wang graduated before finishing all the case studies and all the investigations we wanted to do. But this is one of her simulations that shows the power and potential of vortex methods. The initial state is idealized vortex sheet lying all along a chain of circle of latitude. And Kelvin-Helmholtz instability sets in, it rolls up. A very complicated spirally topology develops. But when there is no rotation, very important qualifier, when there is no rotation, advection automatically moves the Lagrangian blobs just where they need to be to continue to track the dynamics. So even though we're solving a nonlinear problem in 2 dimensions, the Vortex method has essentially reduced it to a 1-dimensional calculation that goes very fast on a laptop. Unfortunately, there are still a whole bunch of difficulties with using these kind of Vortex-RBF methods. And one of them is that when you add in wave physics, advection no longer automatically puts concentrates the numerical degrees of freedom where you need them. The result is that you have to do something else. In the previous talk, the something else was this panel adaptation scheme. Unfortunately, that kind of blows up the meshless paradigm, which RBF people are very proud of, the fact that you need to define a set of interpolation points, but you don't need to construct a topology of subdomains to go along with them. A couple of months ago, I was at a meeting of the Society for Industrial and Applied Mathematics where there was a session on meshless methods. And Robert Krasny was one of the speakers, and I was another. And after the session was over and Robert had left the room, one of the organizers turned to the rest of us and said, "That was a fine talk, but did he know this was a session on meshless methods?" What he meant was that doing that kind of panel adaptation scheme requires you to do exactly what RBF people desperately try to avoid, which is to construct a mesh with a topology that you have to keep track of time step after time step and rearrange as the calculation goes on. We hope that we won't have to do that, at least not for all problems. So in our work, we're experimenting with various adaptation criteria which are localized and point-wise and don't require creating a mesh. Another strategy we're experimenting with, which makes sense only for RBFs, is what we call magic paintbrush. And the idea is that as the flow evolves, a graduate student, or even better, an undergraduate, can paint the screen where more resolution is needed because high gradient regions are developed. And we have a little subroutine that erases the low resolution grid and sprays a higher density of points where the paintbrush is touched. It's very easy and fast to do. It substitutes human intelligence for automatic adaptation criteria, which, as we all know, don't work terribly well. And it works for RBFs because RBFs are extremely tolerant of the grid and don't require a regular grid. Unfortunately, the case studies for our adaptation procedures are still in progress, and I can't discuss them at the present time. Another major difficulty with RBFs is that they scale horribly to large n, because the cost is going up as roughly the cube of the number of degrees of freedom if you do it by the most direct method. Partly this reflects the absence of an algorithm like the fast Fourier transform for RBFs. Partly it reflects the fact that we're doing dense matrix manipulations. Partly it reflects the fact that with spherical harmonics or other standard spectral methods, you can use factored summation to do transforms, which is a highfalutin way of saying that a 2-dimensional Fourier transform, for instance, can always be split up into a sequence of 1-dimensional transforms with enormous acceleration thereby. There are some possible strategies for dealing with these, which I'll talk about in a moment. Another difficulty is that RBF methods become exponentially ill-conditioned as the shape parameter alpha goes to 0, what RBF people call a flat limit. And that's kind of unfortunate because that's also the limit at which RBFs are most accurate. It turns out, happily, that there is a sort of safe operating range, usually alpha around 2/10 to 3/10 for Gaussians, where the accuracy is very good, but the ill conditioning is not that bad. But I kept it on the list because people like Bengt Fornberg and Natasha Flyer and Greg Fassauer have been making heroic efforts to find alternative algorithms that are uniformly valid for all values of alpha, allowing you to follow the limit in which alpha goes to 0 and RBFs transition to conventional spectral methods, polynomials or sinc functions or whatever. Number 4 is that there's still lots of things that we don't understand very well about RBFs. If I have time, I will share a couple of my own personal surprises with you. I've been taking a kind of inverse approach to what Natasha and Bengt and Greg have done. Instead of asking how to get from RBFs to the polynomials, I've been asking how do you convert a polynomial spectral method into an RBF method? But we'll talk about that in a bit. Unfortunately, progress in resolving these difficulties has not been as fast as one might like, because the RBF community is kind of like Lake Wobegon, Minnesota, in Garrison Keillor's imagination, where all the children are above average. There's been a certain lack of urgency in recognizing that these scaling problems really need serious effort, and the ill conditioning is something we should worry about more also. Nevertheless, albeit in tardy fashion, some new measures are on the horizon. First of all, the Vortex people who've been doing Vortex methods for several decades have always recoiled in horror at the idea of working with a dense interpolation matrix. So the Vortex people almost universally have cheated by replacing honest interpolation by so-called quasi-interpolation. And that's a highfalooning way of saying that the overlap between the vortex blobs is ignored, except for application of a constant scaling factor. The good news is that this enormously accelerates the speed per time step because you're not creating and inverting a dense matrix. The bad news is that it totally blows up the spectral accuracy inherent in Gaussian vortex methods and lowers it to second order. And that second order only applies if you've got a grid which is almost uniform. So vortex modelers have to do frequent regridding to get back to a nearly uniform grid, so the quasi-interpolation errors aren't completely unmanageable. We intend to stick as much as we can with doing honest interpolation. Another strategy is called the partition of unity method. It was proposed by Holger Wendland, who's one of the big authorities in RBFs over a decade ago. But again, there's not a strong sense of urgency in the RBF community, so it's only in the last year or so that folks have been actually applying it. The basic idea is to multiply, in our case, the vorticity field by a series of window functions to split the global vorticity field into a bunch of overlapping, spatially localized parts. The partition of unity stuff simply means that the window functions are chosen so they don't make any errors when you do this partition. This looks like a very promising strategy because it splits one enormous matrix problem into a much smaller set of tinier matrix problems, which collectively are still a lot cheaper than the one big matrix you began with. So this will enormously expand the range of problems that we can handle, and it's something we definitely are going to work into our code. Other people have worked on development of fast transforms. As I mentioned, for short-range interactions, they're no good for RBFs. I wrote a paper on that subject, and so did some other people. But for the long-range interactions, such as we have to do when we sum up the velocity contributions, tree codes can help a lot. Well, as I mentioned, I have been doing a lot of work on the fundamentals of RBFs. And one of the questions I've been looking at is to try to understand the connection between the polynomial limit and on the infinite interval. This is the connection with the sinc interpolation. And so I tried to explore the cardinal functions or Lagrangian basis associated with RBFs. And what I found was something quite remarkable. RBF papers can sometimes be horribly tedious to read because there are all these different kernel species around. And so you read 5 pages on Gaussians, and then you read another 5 pages on multiquadrics, another 5 pages on inverse multiquadrics, and it goes on and on and on like a Chinese water torture. But what I found was that when you look at the Lagrangian basis, at least in simple situations, they all turn out to be the same. In the little table, I have listed the kernels for the 5 most popular spectrally accurate RBFs. And what I found is that the cardinal function for all of them has a common form, which takes the form of a Whittaker cardinal function multiplied by a linear factor divided by a hyperbolic sine, with a scaling constant which is related to the shape parameter of the different RBF kernels by the functions given in the right-hand side of the table. Much ado about nothing, all these distinctions. I've been able to extend the theory from the simple idealized one-dimensional uniform grid to somewhat non-uniform grids and to two-dimensional grids, and pretty much the same thing happens. These are plots of a two-dimensional RBF cardinal function. This is actually chosen to be the one that deviates most from my theory, and the deviations are not visible to the naked eye. But I feel like I've kind of walked into an old Marx Brothers film. There's a famous scene where Groucho Marx says to the audience, "Who are you going to believe, me or your own eyes?" Well, the me of the radial basis community is that radial basis functions are, well, radial. But if you look at the contours of this cardinal function, they look square. The grid imprinting has overcome the, well, radiality of the RBF. So from the cardinal function point of view, things look very different. I've also looked at polynomial cardinal functions and RBF cardinal functions on a finite interval, and again asked the question, how do you get from one to the other? There's no theory, so I carried out experiments by taking the ratio of the various RBF cardinal functions to the corresponding polynomial ones. Now, the individual cardinal functions, and you see some of them listed on the page at the left, are quite different from one another. The dashed curves are the RBF cardinal functions, and the solid lines are the corresponding polynomial cardinal functions. But it turns out that when you take the ratio, the index that specifies whether the cardinal function is peaked near the endpoint, or the middle, the left endpoint, or somewhere in between, becomes irrelevant. The graph at the left is actually 17 different curves plotted one atop the other. And you can't tell there's any difference between them. There is the formula is that you can convert an polynomial cardinal function into its RBF counterpart and vice versa, simply by taking this smooth function and doing a multiplication. But there is no theory to explain this phenomena. But it shows to me that there is a deep connection between RBFs and polynomials that we don't understand. There's some deeper reality that we haven't yet grasped. The figure on the right shows the common mollifier function, as I call it, when one uses 81 interpolation points and Gaussian RBFs. And the remarkable thing is that this function can be fitted to within visual indistinguishability by a Gaussian. Again, a very simple, aesthetically appealing result for which there's absolutely no theory. So in summary, RBFs, although I haven't tried to prove it, are a great technology for doing small-scale engineering problems. They are really easy to program. And when you only need 1,000 degrees of freedom, the fact that you're dealing with dense matrices doesn't make any difference because the calculation will still unfold in a couple of seconds on a laptop. So engineers who've got little problems to deal with really like RBFs, and computer graphics people like them for the same reason. However, the kind of problems that we've mostly been talking about here, which are enormous general circulation type problems, RBFs are way, way, way out of the running because they scale so badly, even with the improvements that I've talked about. I also have a number of plans in mind for continuing my research into the fundamentals of RBFs, but since I'm all out of time, I will stop, and thank you.
Question. So you said that there was no sort of fast multipole type approach you could be used directly, but I have heard people talking about the fast Gauss transform.
Well, my paper was specifically about the fast Gauss transform. And the conclusion was it works great for the problems for which Greengard and Strain invented it, but for various technical reasons that would require too long to discuss here, it works horribly for the short-range interactions in RBFs.
So just to clarify, so when you say small alpha, do you really mean keep alpha fixed and then send n to infinity? Is that do you get the same problem?
Something like that. You need for RBFs to be accurate, they need to be wide relative to the average grid spacing between them. And unfortunately, in that limit, the Gauss transform is no good.
Right. So our hands over here.
Are the RBFs, are they global functions or local functions?
They're global functions.
Global
There is a class of RBFs which is compactly supported, but I haven't used them and I didn't talk about them here. but they have been widely used in other applications.
Okay, I think we've
How do you
been-
combine like with existing functions like other spectral basis functions?
Well, that's one of the things that I'm trying to research, is to understand that relationship.
Okay, we better move on now to the next speakers. Let's thank John again.